Hi guys, in this video I want to show you how to build a simple ALU, an arithmetical logical unit. And I also want to explain you what a ALU can do. An ALU has always a few registers. A register is a storage device where you can store a few bits. This ALU just has 4 registers, denoted by register 0, percent stands for register, register 0, register 1, register 2, register 3. And in each of these registers you can store 8 bits. That's why I'm using 2 hex displays for showing its content. But you can do more than just storing data in these registers. You also can do computations with these registers. In this case you can do addition and subtraction. For example, you can add one register to another one and add the result in a third one. And what this device is supposed to do, you can control with 8 bits, basically a 8-bit machine code that specifies what you want to do with this device. And then you have to click the clock, and then whatever you have encoded here as an operation gets executed. Now let me first demonstrate you how to use this device, and then I will show you how to build this device step by step, and by that you will also learn how to use this 8 bits magically to control this device. Let's say I want to store hex 01 in register 1. Then I have to specify hero 1 and hero 1. Then I can press the button and boom, here we have hex 01. Next I want to store in register 2 hex 02. Then I change this here and also this here. Press the button, boom. Then I want to add register 1 to register 2 and store the result in register 3. Then I change it to this one here and press the button, boom, here we go. Next I want to do a subtraction. I want to subtract register 1 from register 2 and store the result in register 3. Then I change the code to that, and that should do the trick. Next I also want to subtract register 2 from register 1. This should give us hex FF, and it also should overflow if you consider this bit patterns as representing unsigned integers. Because you also see that I'm having, of course, here status bits, and you already know the meaning of them. So we should see here, for example, the carry flag being equal to 1 afterwards. Okay, I want to subtract register 2 from register 1, store the result in register 3. Boom. Then you see the carry flag is set. Also the sign flag, because here the most significant bit would be 1. Let me also show you something. This register 0 is actually a fake register. It always contains a bit pattern that only has zeros. That means if you read something from register 0, you always get 0. If you write something to it, nothing happens, except that the status bits will be changed. So here I change, for example, that the result should be now stored in register 0 instead of register 3. Then it seems nothing happens when I click the clock, because the status bits are the same as before. But now I do something like subtracting register 1 from register 2, but store the result in register 0. Then, for example, the carry flag should not be set. I subtract register 1 from register 2 and store the result in register 0. Then you see the status bits are again completely 0. If I want to store the result instead of register 0 in register 3, I just would specify here this 2 bits representing, by the way, unsigned 3. And then you see actually something was computed. Okay, but again, the details about what these instructions are actually doing and how to encode these instructions in here becomes clearer when you build this device by yourself. Okay, so the first circuit that we built is the so-called register file. So let's call this reg file. And the register file is a small memory device, but you also can use this memory device for actually doing computations. And the computations will be added in another circuit. So here I will use D flip-flops, so edge triggered flip-flops, and in each of these flip-flops I can store 1 byte or 8 bits. And because it's a small ALU that we built, the register file is also small, we will just have 4 registers. And actually one of them will become a so-called 0 register. And I will use the term register and D flip-flop synonymously. So in this registers I can store data, 8 bits, so I need a 8-bit input field. I call this data in. Then I also need to specify in which of these 4 registers I want to store this data. So I need 2 bits for addressing a register. And I call this addr in. Then I also need to specify whether I actually want to write something to a register or read from a register. And I just need 1 bit for that, and I call it write. And then we already can do the wiring for that part. So I connect the data with each of these flip-flops or registers. And then I will use a demultiplexer that selects which of these 4 registers gets the write signal. And this demultiplexer has 2 bits for the control input. It gets the write signal and it delegates this to each of these 4 registers. And then I also can read data from a register. And actually, that's special about this register file. I can read data from 2 different registers if I want. So I actually do have 2 inputs where I can specify the address of a register. I call this one here register out 0. I can specify here the first register from which I want to read its content. And then I also need 2 outputs where I can see the content of a register. I call this data out 0. And the second one I call data out 1. And now with addr out 1 and addr out and data out 1, I basically do the same thing twice. Let's begin with the first one with a multiplexer, which I switch to a bit width of 8 and has a control signal size of 2. This didn't work. I can select the first register from which I want to read something. Let's arrange it maybe like that. I need a bit more space for debugging features. So here I can begin with the first register that I want to read. And then I need this part here another time, actually just this part here. And here I do basically the same thing with addr out 1. And maybe I align this a bit nicer. And then I basically just do the same wiring again. So I pick up content of register 0, 1, 2, and 3. And now for educational purposes and for debugging, I also want to have a feature that I can see the content of all 4 registers at the same time. And the registers, for short, I denote with %0, %1, and so on. So I need this 3 more times. So this is 1, 2, and 3. And then I connect this here again with register 0, register 1, register 2, and register 3. And now, of course, we should check things. For example, I want to write something to register 3, then I specify here addr_in as 1, I select some bit pattern, write it to here, then you can see here the debugging feature. Then I write something to different register, to register 2, for example. And then you also want to check out that you now, for example, can see here the content of register 3 or register 2. And here you can pick up another register, for example, here register 3, register 2, register 0, register 1. Okay, so now this would be a simple register file with 4 registers. And we make it even simpler. For now, it probably doesn't make sense, but just think of it as making the hardware cheaper. This register 0 will be an actual 0 register, a register that always contains a bit pattern with only zeros. And if you write something to it, nothing happens. And I do this by simply deleting this register now again. I also don't need this file here anymore. And I simply connect here constant input with 8 bits, where all bits are 0, like that. Okay, and now you see if I write something to register 0, of course nothing happens because actually no register 0 is implemented here in hardware. If I read something from register 0, of course I always get the 0-bit pattern. So a bit cheaper this piece of hardware because we only now have 3 flip-flops of 3 registers with each having 8 bits. Okay, and now we check the layout so that we later can reuse it. I want to have, for example, here this write input at the bottom, and this here is okay. And yeah, this should do the trick. And next I want to have actually a demo circuit where I can check things, and I will call this demo circuit ALU. Now in this demo circuit I need, for example, a push button for executing an instruction. I also need a 8-bit instruction input. Let's call it instruction. I, of course, also need the register file as an essential building block. So let's also insert it here. Then I also want to see the content of register 0, 1, 2, 3 at all time. So I also need hex displays. For example, here I want to see the content of register 0, which is of course always hex 0, 0, register 1, and so on. And then I, of course, also need a splitter for each pair of hex displays because I want to display 8 bits. So I need a splitter which is certainly splitting 8 bits into 4 and 4. And this 3 more times. And then you see the wiring probably gets a bit complicated. For example, I could wire this here to register 0, and here I want to show you a feature from CircuitVerse which makes this a bit more easier to keep track of essential parts without losing the overview because of too many wires. You can use a so-called tunnel for making it simpler. Let me first show you this tunnel with this together with this clock. You see, this tunnel has here an identifier called T, the debug flag identifier. I will change this here into clock. Now I call this part of the tunnel clock, and the tunnel has two endings, two essential parts, entry point and the exit point. And this tunnel here, this ending of the tunnel, or actually the entry point, I want to connect here with the push button. And for that I change the direction to right, connect it like that. And now you see that if I click the push button, I'm also changing the bit here. And this later, for example, will be used for controlling that something gets written into the register file. Because when a instruction gets executed, it will always have the effect that one of the registers will be overwritten with something. So we already can connect this push button here with the right port and make it more convenient. And the same thing I now will do for connecting this hex displays with this registers. So for example, I make a copy of that, which already has the correct direction. I call this here %0 and then change the bit width to 8 bits. And connect this here, for example, with register 0. Then I make a copy of that and connect it here with the hex displays. And like that I connect all the other hex displays. Okay, and now we, for demonstration purpose, can, for example, connect data in and header in so that we actually can check whether everything is working. Okay, now let's say I want to write hex FF into register 3. Then I, for now, have to do this manually here by selecting the data in and the header in. But if I hit the push button, I can see that this debugging feature already works. Now the next thing I want to prepare is basically the grouping of bits in the instruction field. With these two most significant bits, for example, I want to specify a certain kind of instruction. And with the other bits, also grouped somehow, I can specify details of the instruction, parameters. So for that I probably move this here up. And the grouping will also be done up here, and I also will use tunnels so that certain things can be used down here. And then for actually implementing things, I just move this up, do certain parts down here, and go up for checking whether things are actually working. Okay, now about the grouping, I want to have a group of first 2 bits, 4 bits, and then 2 bits. So I need a splitter with 8 bits, split it into 2, 4, and 2. And maybe you also want to use here a bit more space so that above of the instruction field you can use some annotations, which makes it easier to keep track of what bits we're talking about. This arrow in CircuitVerse has the property that basically it's as wide as 2 bits. Okay, now you see, for example, when I'm talking about these 2 bits, I will call it the op bits, which of course have the meaning of identifying an operation or the so-called opcode of an instruction. Then I use here 3 more tunnels. So this here is the tunnel for op, which has 2 bits. The direction should be changed. And here, for example, I pick up the 2 most significant bits. Let's check it. Yeah, this is 2 bits here. Then the next group has 4 bits. I call this here X, Y. And I should change the bit width to 4. And this last group for now has the name Z, and it has 2 bits. And here I pick up the 2 least significant bits. And then later I also want to split this group of 4 bits further into a group of 2 bits called X and a group of 2 bits called Y. So I need another splitter, and I already do this now. So here I make a copy of that, but call it X. Also another copy which will be called Y. Okay, and now you see here the 4 bits that are now 1 belong to the group XY, and the upper 2 bits are these 2 guys, and the lower 2 bits, the Y bits, are here. Okay, and now we actually can think about what kind of operations we want to have. If you see here a 0, it means the opcode is 0, 0. Then I want to sign extend this bit pattern to 8 bits and store this 8 bits then in the register identified by Z. That means, for example, now the sign extension should be a bit pattern with just ones, and the destination register now would be the register 1. So I should get from this bit pattern basically this data in. This is something that needs to be done to make this automatically. And then the effect should be like now when I push this button that I have here hex FF in register 1. So now before we actually can realize that, we need some auxiliary tool for sign extending 4 bits into 8 bits. And I will call this subcircuit sign extend. So for a sign extension of 4 bits, I first need a 4-bit input, I call it in, and a 8-bit output, which I call out. And then I either extend this with 4 zeros, so I change this here to 4 zeros, a constant input field. And if the most significant bit is 1, then I 0 extend it with 4 ones. Now, what kind of extension I actually will use depends on the most significant bit of in. So I have to pick that most significant bit up. So I need a splitter which splits 4 bits into 3 and 1. And then I can use a multiplexer with 4 bits to select what kind of extension I need. And then I have here the extension for this 4 bits. Now I have to assemble these 2 things with a splitter that splits 8 bits into 4 and 4. Here I change the direction, and the 4 lower bits come from the original input and the extension comes from here. And that's it. Now you see if the most significant bit is 0, I just 0 extend this bit pattern. If it's 1, I extend it with this bit pattern that just has 1s. Now this will be a building block that I want to use in a slim way, so I decrease here the height like that. And go back to the ALU and make use of that. Now actually, now we just have to work down here because we can pick up all the signals from above. And maybe I also rearrange here this so that I have a bit more space. The clock is just wired to right. And then I want to first replace here data in with something that depends on the opcode and the bit field X, Y. So I remove this here. I will use a demultiplexer that, depending on the opcode, will make some choice, hardware coded if. So the signal used for controlling what I do with the multiplexer is actually depending on the opcode. So I just make a copy of some tunnel and rename the flag into op. And this here should give me 8 bits that I will use as data in. So I connect this here already with data in. Now what I should get here at port 0 is the sign extension of XY. So I need another tunnel. I first make a copy of this tunnel here, rename it of XY. And then here in between I insert a sign extension. And the adder in, where I want to store this sign extension of XY, depends on set. There's 2 least significant bits from the instruction. So I also will remove this here, and then I will have here a very similar setting. Just the multiplex in this case will be having a bit width of 2 bits. And what I get here, in case the opcode is 0, should be the bit field set. So copy this tunnel here, call this debug flag set, and this should be used as adder in. And here I should decrease the bit width to 2 because set is just 2 bits. Okay, this is adder in. And now things should already work for this type of instruction. And for checking that, I just have to go here to the upper part. For example, if I want to write hex FF to register 1, then I'm specifying here XY to just once. I specify here 01 as destination register. I hit the button and boom, here we have the sign extension. If I want to sign extend 0 and then 3 ones, the sign extension should be 4 zeros and then the bit pattern 0113, and I want to write this, for example, to register 2, then I specify here register 2, hit the button and boom, here we go. And of course, sending something to register 0 will have no visible effect because it's a 0 register. And now we can continue with the next instruction, but let's already prepare a few things here in the bottom. You see, in this particular instruction, I do not need adder out 0 and adder out 1 because I do not need any data already stored in the register file for this type of instruction. But still, I already want to set up things here that in general, depending on the opcode, certain registers will be used as source of a certain input. So this setting with a multiplexer and the opcode, which I also might better align here. No, it was actually aligned. I need 2 more times. So let's make a copy of that. Actually, in this case, set is not needed. But with that here, I want to specify enter out 0, and with this here, actually a bit more below, adder 1. So this here will be connected with adder out 0, and this here with adder out 1. And then you get these red lines because I do not have here a well-defined input. So in this case, I simply use a constant input with 2 bits, specifying the 0 register. It doesn't hurt. It's not needed now, but it also doesn't hurt. Okay, and now we can think about the next instruction. This next instruction will have the opcode 01. And in this instruction, I want to do the following. With set, I specify that a certain register is the destination of a bit pattern. But this bit pattern will be stored after I first left shift the bit pattern that is already stored by 4 bits. And then this gap in the lower half will be filled with XY. So that means, for example now, register 1 should be left shifted by 4. You would not see a difference because you just have zeros. And then the lower part overwritten with 7. If I would apply this operation again, the 7 would be left shifted and the lower part, in this case, again overwritten with 7. So this allows me with 2 instructions to fill a register with 8 bits in total. This will require another auxiliary subcircuit, something which is left shifting 8 bits and then filling up the lower 4 bits with a 4-bit given bit pattern. So I will call this here left shift add, something like that. Here we need 8 bits for the original unshifted data, which I call data in. 4 bits for this 4 bits that I want to use as fill-ins. I call this simply A. And then for the output, we need 8 bits. And I call it data out. Now, in this shifted data out, the 4 most significant bits will be the 4 least significant bits from data in. And this simply can be realized with 2 splitters. Both will split 8 bits into 4 and 4. And then I pick up here the 4 least significant bits, connected with a equal splitter, where I simply just change the direction. And the 4 most significant bits of the output are the 4 least significant bits from data in. And the fill-in comes from here. So that's already it. And now you see, if this fill-in is a 0-bit pattern, you simply left shift this data in. If you have something here in the upper part, this gets discarded. And what you fill in, you specify here. Yeah, and that's it. So let's make this here a bit wider so that we actually can read certain things, and yeah, should be okay like that. And now we can use this in the ALU. And here we just go to this lower part. Focus here. Now here the input for data in actually now depends also on what is already stored in register set. So we somehow need, for example, from data out 0, the value stored in the register specified by register set. Now, in order to get that, I will use set not only for data out, adder in, but also for adder out. And, everything is, by the way, red because I'm already selecting here op 01 and nothing is connected here. So here the destination register, maybe I do first, is also 1. And as I said before, from data out 0, I also want to have set. So I specify here that, follow this wire, adder out 0 is specified by set. That means data out 0 now has the value stored in register set. And then I insert my left shift add circuit. Data in comes from the register set. This here is red because A is still unspecified. And this fill in bit pattern comes from XY. Okay. And then we still have one red line. This adder out 1 is actually not required for this operation, but it's red because circuitverse requires here some valid input. I simply use here again the 0-bit pattern. And this should already do the trick for this type of operation. And then we can check this out. So now I want to use this operation to initialize register 1. For example, with first hex 0, 7. Then XY should have the bit pattern 0, 1, 1, 1. This here will be the fill-in bit pattern. Now if I push the button, this bit pattern gets left shifted. So this 0 gets shifted to here. And here I get 7 as fill-in. And that's working. Now I want to left shift the 7 to here and let's say fill in here a hex 3. You see here XY is now 3. If I push the button, because opcode is still 0, 1, the 7 gets left shifted and the fill-in is 3. And now you certainly should play around and initialize all the other registers. Of course, no effect if you specify here register 0 as destination, because writing something to register 0 is discarded. Okay, and after playing around with that, maybe you pause the video, we do some optimization, which is now not really making sense, but it will make sense when I tell you the next operation will add 2 registers together. This kind of optimization is simply now using data out 1 even for this first 2 instructions. What I will do is I will remove here first this wire and I will add here an adder to data out 0 and data out 1. And I will use the circuitverse adder for that. Maybe here, because you will see later I have to replace it with another circuit that also supports subtraction. The red lines here you get because this adder should be a 8-bit adder. Okay, now what is going on? Before I said we actually don't need, for example, data out 1. I somehow specified that adder out 0 and adder out 1 is always specifying the 0 register if the register is not actually needed. That means if the opcode, for example, is 0, 0, we simply compute here the result of register 0 plus the result of register 0. This result is anyway not needed if the opcode would be 0, because then we don't need it. If the opcode is 1, then we actually just need data out. Now we actually have data out plus register 0, but because register 0 is a 0 register, no harm done. Still works as before. Also check it out. But now we can implement easily the next instruction with opcode 1 0. 1 0 should have the effect that register X gets added to register Y and the results get stored in register Z. So that, for example, means if I'm specifying here a 1 and here a 2 and here 3, then I want to add register X to register Y and store the result in register Z. And of course 1 1 later will do a subtraction. But for now let's focus on the addition. And here it pays off what we already built, and I probably can close here this dialogues. We simply have to go through all the multiplexers and somehow set up correct inputs for the port 2. Okay, and here it makes actually sense to fill up this table bottom up. Let me zoom this things. If the opcode is 2, then I want to add register X to register 2. And that means I need, for example, here add data out 1, the content of register X. That means adder out 0 should be X. So actually I do need here the properties. This here should not be X. And with this here I specify the operand B for the adder. And I want to add this to register Y, and register Y gets specified here with adder out 0. So I'm changing this here to Y. And connect this with 2. And now that means here I have register X, the content of register X, here the content of register Y. I add it together. This will become my new result that I want to store in a register. So I now can connect this here. And in which register data in, the result, the computed result gets stored, I specify here. So this will all also be set. Now here we actually already can consider what we will do next before I actually show you that what we did is already working. With the next operation, opcode 3 or 1 1 in binary, I want to do a subtraction. I want to subtract register X from register Y and store the result in register Z. And that means this here will be replaced by some tool that can flip between addition and subtraction, something that you already built. That means here the wiring will actually not change too much, except that I replace this tool and have a new bit selecting things. But for example here the operands still are the same. Content of register X will be also here. And also register Y here. And the destination register will also be set. And then you see here, this is actually a waste of money to use here a multiplexer. In every case, we simply select here set. So let's optimize this and simply connect here set. Then it's also a bit nicer to read things. And the result that comes from the subtractor also will simply go into here. So you have this wiring. Okay, you already can do this now, but now we should check whether things are actually already working. And for that we just need this upper part. So first I initialize some registers. For example here I want to have hex 01. So I can use the operation with opcode 00 and store a hex 01 here. Bam. Then here, for example, I want to store hex 02. Can use the same opcode, specify here destination registers 2 and the bit pattern for hex 02 given here. And now we can use our addition with opcode 10. I want to add register 1 to register 2 and store the result in register 3. Register 1, add it to register 2, stored in register 3. Boom, now it's working. And now, of course, you also can use the other operations. For example, if I want to change this here into hex 1F, then I could first left shift register 1 and then fill up the 4 lower bits with XF. And then you can go back to the addition, add register 1 to register 2, store the result in register 3, and so on. Okay, but now we have to think about replacing this building block, something that we already built before. This will be a new sub-circuit that we insert here for doing either addition or subtraction. So something like add/sub will be the next sub-circuit. And here we need 8 bits as input, and I will do this very quickly because you already implemented that. And this gives us the carry flag, and here we have the computed output. And then, of course, a similar way you can add here status bits for the overflow, the sign flag, and the zero flag. Something that you might want to do on your own, or reuse your own circuits for that. Okay, now let's check this building block. Yeah, can be used like that. Okay, and now we insert it here, maybe a little bit more to the right, because of course this also depends on the opcode, whether we want to do an addition or subtraction. So the output comes from here. And then we need a multiplexer. That, depending on the opcode, gives us a 0 or 1. And that means here we have 1 bit. And in the first 3 cases, we can use this as an adder. In the first 2, we can use it as an adder or subtractor. In the last one, we certainly have to change this here to 1. Okay, and that's almost it. Now maybe we also want to pick up here the carry flag. This needs some additional work. Let's put it up here that we can see it together with the results. Okay, now we first initialize here register 1 and register 2 with something simple, like, for example, 1 in register 1, 2 in register 2. Then we do again an addition. Register 1 should be added to register 2 and the result stored in register 3. Then we want to do a subtraction. I want to subtract register 1 from register 2. So I should get hex 01. And this simply means I change the opcode to 3. Then I get hex 01. If I want to subtract 2 from register 1, then I have to change things. And afterwards we should have an overflow, because that would give us hex FF. And if it's signed, an unsigned integer, then this should set the carry flag. So this should go to 1. So register 2 gets subtracted from register 1, and the result stored in register 3. Now you see here what needs some additional work. The carry flag is already indicating that after I hit the clock, I would have an overflow, an unsigned overflow. But actually I want to have this visible only after the instruction was executed. And because this here is already computing the result before it actually gets stored in a destination register, this shows up too soon. So what we actually do need here is another flip-flop, a flip-flop which is buffering the status bits that are computed by the adder. Let me show you the effect again when I use here a single flip-flop. And maybe I also use here a tunnel so that I can pick up things up here. So I connect this carry flag with a flip-flop. This flip-flop also needs to be triggered by the clock, and that means I need a tunnel for the clock, or I actually can pick up this here by wire. And then this here will be changed after the clock is hit, because before I do not have a positive edge of the clock. And here I will use another tunnel so that I can show you this above. So I call this here not zero flag, carry flag. And then I copy this here up here, change the direction, and connect it with a button. Okay, now here somewhere is the bit width wrong. There should be 1, and now we should be good again. Okay, now let's do the same thing once more. I'm initializing register 1 with a 1, register 2 with a 2, then I subtract register 2 from register 1. I prepare the operation. Register 2 should be subtracted from register 1, the result stored in register 3. And now you see the carry flag is still 0. I hit the clock, and after I hit the clock I see the new result, and I see the updated carry flag, because the flip-flop is buffering the information. And in a similar fashion you have to buffer all the other status bits in a single flip-flop. But that's something you certainly can do by your own. So this here is in a simple way most of the ALU project, and the rest we can do together.